All right, so in your nitrogen cycle, the sheet that I just handed out, we're gonna go over where these processes occur. This is when I didn't print those out last week. That's been on my mind all weekend to make sure that I print these out so we can go over this. So fixation, and they should be numbered. Fixation is atmospheric fixation. We have these rhizobium bacteria that fix nitrogen from the atmosphere and supply a plant available form to the soybean or some legume crop. This typically happens with legumes. I didn't have that one fixed in. Mineralization. Mineralization is the transformation from organic to inorganic. And as part of that mineralization, it's a two-step process. Because when we think about organic, although organic typically has some carbon involved in it, but amines are also organic. That's where we get our amino acids from. Our amino acids turn into proteins. Proteins give us muscle. Same concept for plants. It's how they get their energy. It's how they get their strength and their resilience. Next we have nitrification. And then plant uptake. So the two plant available forms, ammonium and nitrate. Those are the only two plant available forms. Once it becomes ammonium or nitrate, the microbes need it. And so if mineralization is the conversion of organic to inorganic, what do you think immobilization is? If mineralization is organic to inorganic, or inorganic to organic, immobilization, inorganic to organic. These processes, mineralization, plant uptake, and immobilization, occur in just about every cycle we're about to go over. So when I ask, what is the fate of phosphorus, you should at least get those three right. Those should be instantaneous, you at least get 3 points. Immobilization, mineralization, plant uptake. Key to what we do here. If it doesn't get immobilized, it can either be leached into the groundwater or through runoff. I would not hang my hat on the fact that nitrate gets trapped in between those clay layers, because the overall net charge on soils is what? And what is nitrate? Nitrate's negative. So think about that. Think about two magnets, one positive and one negative, that spread apart. Do you think, actually it's really kind of like two negatives. So when that spreads apart, when that expands, do you expect a negative anion? Do you expect an anion to find its way in between two negative sheets? No. So which one of those plant available forms do you think is going to be trapped inside those clay layers? The ammonium, because it's positively charged, right? I try to give a lot of 50-50s. One or the other. And then finally, the parts of this nitrogen cycle that are gaseous losses to the environment are going to be volatilization and denitrification. So if you can think about this, even going all the way back to chemistry, that there's going to be a push to the left or a push to the right, and it all depends on the soil environment. And if you have one this way, such as mineralization, then you're likely to have immobilization. Those two are two processes that left and right of center. Much like nitrification and denitrification. So we're trying to get this big cycle so that we can get the N2 gas back into the atmosphere. Because ultimately what happened, if we're not talking about a legume system, if you take soil fertility, we'll talk about this Haber-Bosch process. And it's a very intensive process where they collect the N2 gas out of the atmosphere. We've got to fix that. It goes through this energy intensive process, and guess what we need for energy? How do we get our energy?
Food.
No, like other kind. How do we get our electricity?
Water.
Huh?
Water.
Sun.
Magnets.
Huh?
Magnets.
Okay, we got magnets.
Yeah.
What's the cheapest, easiest way to get electricity?
Solar and wind.
Okay, so those are all renewable resources. What about the non-renewable?
Oh,
Coal, right. And so fossil fuel combustion, or gas or petroleum, and guess what we just had a little problem with, right? Didn't we shut down a gas pipeline? And what did that do to fertilizer prices? Through the roof. Because we need that energy from that, we need cheap energy to do this process. So now it costs the fertilizer manufacturer a lot more. Guess who ends up paying the final? You do. Correct. Right? So that Haber-Bosch process is how we get this nitrogen out of the atmosphere. And we got a ton of it up there, more than a ton really, 79%. Well, once we apply it to our nitrogen cycle, right here, with our fertilizer, once we apply it to the fertilizer, we want to get that nitrogen back into the atmosphere so we can recollect it. So some people might say this isn't sustainable, but we pulled it out of the atmosphere, converted it into a form we can put on our plants, and then it ends up back into the atmosphere. Well, except for if it gets taken up by the plant, so that part's not necessarily so sustainable. But the rest of it that's in the soil, we need to get that to finish this conversion process back into the atmosphere. So here we have our fixation. This is the mineralization and mobilization process. We undergo mineralization, ammonization, to ammonification that can be taken up by the plant. Ammonium will undergo nitrification, just as part of the process of being in the soil, to nitrate, which can be taken up by the plant or leached. I wasn't crazy about the way they had this thing numbered. In this soil solution, the microbes are going to need that nitrogen when our carbon to nitrogen ratio gets above what number? 24 to 1. When we start pushing that 30 to 1, and we have more carbon in the soil, more carbon material residues like corn plants or stalks, roots, any of that other organic material that we talked about during decomposition, the microbes need that nitrogen in order to have the energy to break that down or decompose it. Guess what? If the microbes have it, guess who doesn't? Or guess what doesn't? The plant. So we have this balance where we want to try and keep our carbon to nitrogen ratio and our residues low. But we're also trying to sequester carbon from the atmosphere as part of mitigating or slowing down climate change and carbon sequestration and trying to balance out the atmosphere and all this stuff. So we're back and forth, we're shooting ourselves in the foot one for the other. Right? So we don't win this thing. We just manage it better. So next, we have this plant uptake. or it can be leached, and then we have these gaseous losses. And so denitrification, something that we would go over in fertility, but basically once it becomes nitrate, we undergo this reduction process, and this typically happens in an anaerobic system. If you'll notice, we are losing oxygens to get back into gas. And so if there's no oxygen, it's a reduction process. So we need to have an anaerobic environment. How do we make soils anaerobic? Kyle's like, what? Flood. Exactly. Flood. We take all the oxygen out of it. But even if we did flood it, just like we had these 9-inch rainfalls, like that filled the soil profile very quickly. But there's still oxygen in there, so that's going to take a little while for that oxygen to be used and dissolved and taken for other things. But once it stays flooded, like maybe in a rice situation, you would have denitrification. If the water evaporates out of the rice paddy before that process continues or finishes, then we have nitrous oxide being released into the atmosphere that is, does anybody remember how much greater it was than carbon dioxide? 300 to 1. 300 times greater. This ammonia volatilization happens when you apply, let's say, urea to your pasture on a hot day. Yep, that's what we do all the time, don't we? That's how we do it, right? That's what we do. We got to apply it when we apply it. Maybe sometimes you might even do it like in the morning time when it's not so hot because it's hot and there's dew on the grass. And you go to apply that nitrogen, that urea fertilizer, there's a little bit of water that starts a process. If that process doesn't complete and get into the soil, 30% of your fertilizer goes into the atmosphere. So you go, yeah, damn, right.
I didn't know that.
Huh?
I didn't know that. I knew it took water to dissolve.
It does, but if it doesn't make it into the soil, it's on the surface, and there are some processes that happen where that can evaporate or volatilize into the atmosphere. So you go to apply 100 pounds of nitrogen to your bean crop or pasture field or whatever, it's early in the morning and the conditions are just perfect for this volatilization process to happen, you only applied 70 pounds, but you paid for 100. The fertilizer prices are doing what? Through the roof. Oh, I know, right? I know. I paid for 100, but I only got the response for 70. But Natras, you told me to apply 100 pounds. Yeah, when did you apply it? These are the kinds of things that you'll be asked to do when you get to your job and you're the consultant or you're the expert on this thing. Right. And so guess what producers do? Instead of trying to figure out a way to minimize that, because there are some ways, we'll just put 130 pounds out. Well, guess what? 30% of that 130 just got lost. So now you paid for more, and you right. My man over here knows exactly what I'm talking about. Doesn't make sense, does it? Doesn't make one bit of sense to add more nitrogen, you're just going to lose again. Doesn't. But that's what they do. That's what producers will do. And trying to convince them any otherwise, how many of y'all have a dad that farms? Can't tell them anything, can you? Until you start hitting that pocketbook. And then maybe they'll listen, but they'll want to spin it around like it was their idea. As if they came up with it. Don't they? Yeah. But anyhow, at least you know, right? At least you're aware that these things are going on now. And then you go, oh crap. No wonder I can't make any money because I'm wasting it to the atmosphere because I haven't sat down and done the math. I'm trying to figure out how much fertilizer I need to apply. All right. Did most of y'all get the nitrogen cycle filled out from while we were going over that? Because it kind of went in order, right? The phosphorus cycle and the sulfur cycle don't necessarily have that numbering, but we're going to follow the same pattern. We're going to start on the right side with some sort of mineralization, We went over biological fixation. Y'all remember this from class? Is this, Jacob, where did I leave off last week? Gotcha. Y'all make sure y'all know those two species. So I guess here we go. Let's step back to nitrification. All right. So we've undergone this is mineralization and part of ammonification. And so next we have this ammonium that is either in the soil solution, and when I say in the soil solution, I mean like dissolved in that little bit of water that is filling up some of that pore space. And so then, if we have a very like sandy soil, there's a lot of oxygen in there, and that will undergo an oxidation because there's oxygen. It's chemistry, fun stuff. So we undergo this nitrification process, and that is carried out by these two species. And so remember we said that the nitrous ammonious converts ammonium to nitrite, Nitrite. But nitrite is toxic to plants, so we don't want this to happen. Luckily, our friends Nitrobacter are going to transform nitrite into nitrate. And I know that I gave you this nitrite into nitrate. So Nitrobacter converts nitrite to nitrate. In order for nitrification to happen, you gotta have ammonium. And so we need a lot of oxygen because it's an oxidation process. Can't have oxidation without oxygen. Aerobic environment. The pH you're going to want, and that's more of a fertility thing, like a soil chemistry. I'll sit there and show you why the reason we need that, but it's not necessarily pertinent to this class. But the pH should be, and for more nitrification, you would want to have a higher pH, 7 to 8. So I think we made it down here. I was mentioning to y'all about methemoglobinemia. It's called blue baby syndrome. And so back in the 70s, moms were ingesting this water that had high levels of nitrite and nitrate. It took up the oxygen because when you drink nitrite, we want it to go to nitrate. So you need the oxygen, and the only place to get that from is from our bloodstream. So the nitrite in the water was taking an oxygen to like balance that molecule out. So they finally found out that the maximum contaminant level for nitrate is 10 parts per million, which is not a lot. That is really not a lot. So that's kind of the purpose of our water treatment facilities, is to make sure that these maximum contaminant levels are all met. And they take a lot of special equipment, reverse osmosis, some membrane type stuff, and some environmental engineering over at Prescott Hall. They got all the real cool fancy machines. I'm gonna go drive the tractor, and I'm gonna cut some stuff down, and then I'm gonna fertilize it again, because that's what I do. Okay? That stuff is cool. I love being over there. If you know how to run one of those machines, you ain't running the show. And that's how I look at that. But that's not for us. We like being outside. We enjoy making something we can see with our hands. So there's that part. Next, we have the plant uptake. That is going to be central to all of the cycles, because that's the whole goal. So we can apply these different fertilizer types that have to undergo some process that release this plant available form of, whether it be nitrogen or phosphorus, that P2O5 or K2O, those things we've been learning about in the lab. Come on. We talked about immobilization because if there's a lot of carbon residue in that soil, the microbes are going to need energy in order to decompose that carbon. I still hate putting numbers like this up because the guy who wrote that big book, the guy who wrote the book that I got all this information out of, who's well renowned and well known, I'm going to trust him better than this PhD who just graduated last year, as if I know more than this guy does. So 24-to-1 is ideal. If we get a little bit more than 24-to-1, then we're going to have that immobilization. So right at about 25, somewhere between 25 to 30, it might vary depending on soil type or microbe or whatnot. But let's just make it simple and say that if we start getting above 25-to-1, we start getting a net immobilization. So whatever nitrogen you applied, and you lost 30 pounds of that to the atmosphere, and then it gets converted to ammonium, and then the microbes also need about another 15 or 20 pounds of that because you've got a lot of carbon residue in your fields. You paid for 100, the response you got was for 55. Ow! Ow, you mean half of my product just got lost? So having an understanding of these things help you manage your systems better. We talked about the nitrate leaching. This is where our 4R nutrient stewardship comes in. And what are the 4 R's? The right place, the right time,
Right, ready.
Not ready.
the right rate. And one more. The right source. So applying a source that doesn't have volatilization, that doesn't have to undergo that process, helps to save a little bit there. If we can have a source that converts directly to ammonium, like let's not apply calcium nitrate, or you can't even get ammonium nitrate anymore. Let's not apply something that already has nitrate in it, because guess what's going to happen? And why does it leach, Stephen? It dissolves, and then what? What about the charge?
That's negative.
And what is the overall charge on soils? And so negative doesn't like negative, and it will leach out easier than ammonium being held to the soil column. Bless you.
Thank you.
So in irrigated systems, you kind of need to know this because we're applying water every day, like a golf course. And guess what happens when you apply that fertilizer? That water is moving that through the profile quicker. And if it's not in the profile in the soil, it's not in the plant. This 2-to-1 clay fixation. Remember we talked about being trapped in those inner layers. Volatilization. I don't know, I guess I did, so I did my master's degree on this nitrogen cycle, like this is my baby. So, that's why I get a little like, oh, we're gonna go over this enough time. It's the most important one you'll ever face. It's so dynamic. All of these things occur at the exact same time. It's possible. There's a lot going on. You are absolutely correct. And so understanding that plays a big role because nitrogen is the most important nutrient that we put on our crops. It's the one that makes them grow because it's got the energy. Amines, proteins, growth. So I guess for me, when I apply fertilizer, the very first thing I think about is it going to volatilize? So that would have been first. Application of fertilizer, potential loss to volatilization immediately. There are some chemicals that you can apply to your fertilizer, like Agritane. There are some enhanced efficiency fertilizers that I'm going to be looking at in a pasture situation that stop a lot of this stuff from happening, or at least slow it down a little bit. All right, y'all remember way back when I talked about pH dependent charge? We talked about that when we add lime, we increase the hydroxyl content. I know it's tough. When we talked about the hydroxyl concentration, and remember that one of those hydrogens on that functional group of organic matter dissociated from that functional group and then bonded with the hydroxyl to form water? It's the same principle. In order to balance this equation out, this hydrogen that has we have a +1 charge right here, one of those hydrogens will dissociate and bond with that hydroxyl to form water. But this ammonia, AMMONIA, maybe your grandma cleans with ammonia. Y'all know the smell I'm talking about? The kind, like it's in, Grayson's like, yeah, I know now. It's in smelling salts. That's what they do. They break that cap open and it causes that ammonia reaction. And you're like, oh. That's the stuff you don't mix with bleach because it'll tear the paint off of your walls.
Some strong stuff.
Some strong stuff. And if one's good, two's better. Let's get ammonia and bleach and let's clean this place. So, ammonia is a gas. You can smell ammonia very, very distinctly. It might be a minute before you can react to it. You know, clear your eyes out because you're like, oh, goodness. I mess with a lot of ammonium hydroxide. Those are some cool chemistry experiments, but man, you want to talk about if you get a good whiff of that, it'll shut everything down real quick. It's like one of those, oh, put everything down and step away and try and get another breath. It will literally take your breath away. It will. It will suck all that oxygen out, kind of like through this process. Because that ammonium, that hydroxyl is looking for something else to bond with. So if we can keep our fertilizer as ammonium, it's held to the soil better, right? Because the charge on soils is negative, the charge on ammonium is positive. Now we've got opposites attract. So our whole goal is to keep ammonium in the soil, but keep it as ammonium so it stays there. I actually put this slide in here as a reference. It's something that you can take back with you. Like, it's not only my job to teach you some information, but it's also to give you some information and resources that will be useful in your job. So, we got a high soil pH, and I'm gonna come over here to Michael because I know you're probably looking at this one. That looks like a pasture field we got. With a little bit of moisture and some dew on a low CEC soil that we broadcast fertilize, and we get this loss of volatilization. But if we apply it and get some rainfall, that's the whole purpose of why we want to apply fertilizer right before it rains. Unfortunately, Mother Nature knows we're doing that, and she decides that, you know what? Yeah, I missed it. Cool. Keep on going. So, kind of how that works. But if you can get, about a ½ inch of rainfall right after you fertilize, that process that we talked about, that urea hydrolysis does that conversion where we get this nitrogen prill that turns into ammonium, ammonification, and that waters it in where it can be held by the soil. If it's sitting on the top, it's not protected by the soil. So if it's sitting on the top, it has better chance to volatilize.
It's probably why IMC is so much better.
By what?
Why IMC?
What is IMC?
Manufactured, not the blend. What you get, come on, it's all made together.
So, it comes as a blend?
Yeah. Well, never.
They might add something onto that.
It's
excuse me, that stops that, like a urease inhibitor. Okay, let's think about another thing. Where's that fertilizer sitting at the co-op? And if it's in a building, we're good. I'm talking like the bulk fertilizer. Out in the heat, right? With all the moisture, it's hygroscopic, which means that it's going to attract the moisture out of the air. So now you thought it was 0.46. It's really like 0.4. So you thought you were putting out 100 pounds just to start. Maybe it is, maybe it isn't. All I know is that, like, when I think about these things, I go, and you got this fertilizer sitting out in the heat that's pulling in that moisture.
So it tests heavier than it actually is.
That's less than it actually
Or,
is.
yeah.
Because you're losing some of it. I don't know what the real percentage is, but my thought process says, if you got this fertilizer sitting out in the heat, it's taking in water, and this process is happening, it's probably not 0.46 when you get it to the farm. There's a chance. Maybe it's like 0.43. If you do the math, you did for 100 pounds, 100 over 0.46 is 217 pounds of this 4600 fertilizer. But if it was really 0.4, what is 100 divided by 0.4? You would have needed 250 pounds. You only got 220. Does it make a big deal? Does it amount to a hill of beans? Man, when you got 1,000 acres on the line, it does. Each one of those pennies count. So it's just something to think about, that I think about whenever I'm doing this. I know, man, kind of go, ow. Maybe we need to relook at some books. Maybe we need to relook at some management strategies. Now, I'm not saying that they happen, but as a scientist, it's very possible that it does, or that it might. That stuff keeps me up at night. And then finally, we have this denitrification process where, under anaerobic conditions, that nitrate loses the oxygen. I'm trying to keep this kind of very simple. It loses the oxygen, or it is reduced back to N2 gas. We want it as N2. Now, once it gets off into the atmosphere, that's not our responsibility, because there's oxygen up there also. So we can't stop this top part. See how it goes from N2 to NO to N2O above the surface, like in the atmosphere? I can't do anything about that. Okay, that's Mother Nature doing their thing. I'm responsible for everything below the soil. So we want to get it back to N2 gas so we can keep this sustainable thing. And when I was in grad school, I had to give this a very similar presentation about this bioreactor. My major professor, or not my major professor, I took soil and water. And he said, you're a grad student, I want you to give this thing on nitrogen, these bioreactors. And y'all, I'm thinking it's Mike Rowe. It's going to be dirtiest job. He's going to come in with these hazmat suits. And it turns out it's not. What they were doing is they were taking the drainage water off of a cornfield and putting it into a big ditch that was filled with wood chips. And the wood chips supplied the carbon source for the microbes. And then they also took up that oxygen that completed this process. Like, rather than run the risk of keeping it in the field, maybe I get some, they created an anaerobic environment to complete that process. So, like, not everything has to be done the way we typically would think, like in a waste treatment facility. There are other options, kind of like biological controls. Anybody heard of that? You release ladybugs into a greenhouse to eat the aphids? No, hadn't heard of that, huh? Okay, that's cool. That's what we're here. That's what we're here for. We're even just to think about that concept. Rather than spray pesticides, you can get ladybugs, and that's a money-making gig right there, right? Because all you got to do is just let them do their thing. They're insects. They grow fast, and then you just get to sell them. And if you like ladybugs, it's even better. All right, not that you necessarily need to know the equation, that's for soil fertility, but this is the process that it undergoes. This is the reverse, the reduction of nitrate back into gas. And so if we get all our water moves out, or we have a good drainage, and this process starts, which it might take a little bit, but finally once the water recedes, and if it stops right here at this N2O, before we get to N2 gas, because this is the final oxygen that needs to be stripped out of that. 300 times greater than carbon dioxide. And so this is where ag gets the bad rap, because it's 300 times worse. All right, well, then you get into methane and all this other stuff, and like now it's a whole big thing. But we're really trying to make sure that we don't put this N2O gas back into the atmosphere. Just to look at a couple of the microbes that will conduct this, or complete this process or work through this. So we talked about the Nitrous amonis and the Nitrobacter being oxidizing bacteria. These are reducing bacteria. They reduce, they take the oxygen off. Oh, doubled that up. There are going to be some other environmental factors that are going to play into this. So environment is important, and understanding what your environment is, you can almost kind of figure out, or maybe this is going to occur. So now not only did you apply 100 pounds, and let's say you lost 30 pounds to the environment, and it finally became ammonium, it underwent this process very quick because your soil has a lot of Nitrous amonis and Nitrobacter, and then it rains, and then now you're losing a pound of N per acre per day. You're typically going to find this mostly in like clay soils, because sandy soils are the water is going to drain out, so you have more oxygen, you don't have to worry about this process. A pound of N per day. This probably isn't happening in your pasture feeds. Not likely. All right, so there it is. That's the big thing. That's going to be like on the final exam, be able to fill this out and have some knowledge of it. The questions are going to be what happens, what is immobilization, what is mineralization, things like that. For those of you who are brave enough to move on to fertility, we'll go into this a lot more in depth, and then you'll have to write all that stuff out. It does look like that fertility class is probably going to make, we got a lot of people who need that. Just some basic information about the things that you need to be thinking about when you're applying nitrogen fertilizers. And there's one of these for everyone that you apply. We want to minimize that loss to environment because we paid for it. We paid for it. It's like taxes. We're not getting the taxes out of that by the environment taking it back. We're trying to keep it in the soil so the plant can get it. And that all really comes down to, for our nutrient stewardship, right source at the right rate, the right time, and the right place. All right? Before we go though, if y'all would, please help me sing happy birthday to Madison. How old are you, Madison? 22. 22? Woo! And happy birthday to